Dear participants, in this session we will be closely observing how position control can be achieved in a DC motor based robotic system. As you know that none of the industrial robots nowadays employ a DC motor. However, this experiment looks forward to give us a conceptual understanding of the subject, that how we can use simply potentiometers and the basic concept of servo can be generated in our mind. Nowadays all industrial robots are having high precision servos with encoders in them. Therefore, maybe this particular performance does not have relevance to the industrial robots in particular, but this concept of servo mechanism is definitely important to give us an insight that how position control can be achieved in DC based system through feedback mechanism. Now let us get into the training board. This is Scientech 2453 DC position control trainer. As you can see here, through this switch we can either have a square wave at the output means this pin where we actually connect the motor, okay, and if I keep the switch in on the reference side, then we can generate a reference voltage. Now the point is how we are going to generate the reference voltage. Let us have a close look in this dial. This is basically a 360-degree potentiometer, okay, and we also call it a servo pot. You can see here there is inscription of angular displacement 0, 10, 20, 30, 40 like that up to 360. Whenever we are actually putting this dial at certain angular position, what we do actually, we develop here a voltage. In order to get this concept clearly, let us try to recall the construction of a potentiometer. A potentiometer has got three terminals. Two of the terminals, the end terminals, they are connected to supply and ground, and the center terminal gives us a voltage if we apply the supply voltage to the extreme end terminals, okay. So you know that as we rotate the shaft of the potentiometer, the voltage changes gradually. So from that we can have very easy idea that here some voltage will be generated. Now this voltage is fed to one input of an error block. You can find here this error concept of error block is very common that you have gone through in your process control engineering paper. Now the same error block is used here. Complex electronic circuit has been used inside, and now you can find from the motor terminal we are also having a feedback signal. So this feedback signal we can measure at this point, and you can see this feedback signal constitutes another input for the error block. So now you can understand that the angular command, whenever I rotate this knob, I actually give an angular command. Now this angular command produces a proportional voltage, and this voltage is compared in the error block with the feedback signal. If there is a difference in between the feedback voltage and this reference voltage, an error signal is generated. Now you can find that here is a controller. This controller actually controls the gain, right? The gain in the manner that if this signal is too small, it improves the strength of the signal, and that signal is ultimately can be measured here, and it is fed to the DC motor driver. Now you can see that here there is a potentiometer that we have seen. Now where is the DC motor? Let us look into the construction of the output block. You can see here is the servo pot. You can see this is the servo pot. There are the 3 terminals. Now a dial is attached to the pot that shows different degree inscription 0 to 350. Alright. Now you can see the shaft of this servo is mechanically coupled to a DC motor. You can find here it is coupled to the DC motor. Now you see that whenever the DC motor driver generates a signal for the motor starts rotating. As the motor starts rotating, definitely the potentiometer also rotates, because shaft of the potentiometer is coupled to the shaft of the motor. As the potentiometer rotates, you can see that dial, degree dial, that also rotates. I will just show you one demonstration. You can see it rotates. Now when this rotation of the shaft of the potentiometer takes place, that is the shaft of the potentiometer rotates, you can find here the 3 terminals of the potentiometer. 2 terminals are dedicated for supply and ground, and the center terminal, as the shaft rotates, it generates a voltage. Now you can easily understand that this voltage is actually the feedback voltage that is going to the feedback block. Now this feedback voltage is available here at 0.4 and the reference voltage is available at 0.1. It comes to the error block, and finally the output, summation of them takes place. They are subtracted, definitely, these 2 signals, and the output is available at the end of the error block. Now I will go for another experiment to have a further clarity on this concept. Now, in order to have further clarity on this potentiometer based position control, we will be taking help of this potentiometric error detector setup. As you may please find that here there are 2 potentiometers. Both are servo potentiometers. They can be rotated by 360 degree. The angular displacement can be seen from this window. Same here. It can also be rotated by 360 degree, and you can have the angular displacement from this window. Now very simply, both these potentiometers have been supplied with very stable and same DC power supply. That means that the potentiometers are at exactly same DC condition. Now the wiper terminal of both the potentiometers are connected to this error block as the 2 inputs of the error block, so that we can have the resultant error signal in this point. Now what we will do very simply, we will try to read the difference in this signal that is generated here when there is mismatch in the angular position of these potentiometers. So I will keep one of the potentiometers as reference and the other I will change. Okay, so I will connect this to the voltmeter. So I will make fine adjustment so that the output is absolutely 0 at the beginning. You can see this is very precise arrangement, you know. And you have to be very careful that we do not come across any parallax error. That is quite common. So what I will do, I will first set an angular position of this potentiometer. So let us make it 80 degree. You may not be able to see the reading here, but you can count on me. I have kept it perfectly at 80 degree. Now this potentiometer is at 0 degree right now, and you can see this is the error signal. Now I will be going in anti-clockwise direction towards 80 degree angular displacement. You can see here I have just reached 80. Okay, yes, and you can find almost it is 0. So here you can find that when both the potentiometers, right, they are servo potentiometers and under identical DC biasing condition, when both of them are at same angular displacement, then only you get no signal out of the error block, provided that wiper terminals of both the potentiometers are connected to a very precision error detector. Now let us see another thing. I will take this potentiometer again at 0. This potentiometer is at 80. Now I will be going in clockwise direction to achieve 80 degree. So you can see here we are also getting help of the polarity sign. So the direction of rotation can also be understood from the sign that we are getting out of the error detector. So this is the basic concept of potentiometric error detection, and if we give this error signal to any DC motor, the necessary driver unit is required, because 0.51 volt, minus 0.51 volt can never be adequate to drive a DC motor. So you need a driver unit for that also. So the driver unit will rotate this potentiometer, because this is the reference one. It will rotate this potentiometer so that it rotates in such a way or manner that the error tends to be 0. This is the basic concept of potentiometric error detection. Okay, so I will again get back to our DC position control system, and right now you may very easily understand that it is not possible to go for entire view of the unit, because this dial, it is very small. So what I will do, I will closely focus the camera to the dial, and then I will be giving certain angular command, and I will be dictating the command. We will see whether the dial can reach its destination or angular displacement is made according to the command. Okay, so let us get back to the DC position control system unit. Now you see, if you go to the experimental manual, you will find that there are two experiments, experiment 1 and experiment 2. So what the two experiments signify, let me tell you. That you can see here there is a gain controller. As we had already discussed, this is the gain controller. In the first case, we will keep this knob at fixed position the controller will be at fixed position, and then we will see that how the angular displacement command is obeyed by the motor unit. In the next experiment, we will have 3 different values for the controller position. First, we will keep it at, maybe if I consider this to be the starting point, at this position. Next, I will increase the gain at this position, and finally I will increase the gain at this position. And then we will see how this affects the rotation. Now you see, since there is no dial or similar sort of arrangement, I cannot precisely say that what is the gain value. But gain value can definitely be calculated by dividing voltage at terminal 3 and voltage at terminal 2. However, you have to remember that whenever you apply the gain, okay, the motor starts rotating and it tries to make the feedback signal in such a manner that error is 0. So this computation of this gain is very critical because it is going to be a dynamic factor. Alright. So because this signal, dynamic factor means the gain will not be dynamic factor, but the voltages at this 0.2 and 0.3, that will be a dynamic factor. So it will be hard to estimate, but still we will try. So now this gain controller knob is not going to be changed in its position, and you can see here I have focused the camera onto the motor dial. There is a pointer over there, you can see it is right now somewhere near 350 degree. So now what I will do, I will apply an angular command. You see that right now the dial on the board is at 340 degree. I am rotating it counterclockwise to 230 degree. Clockwise. Now you can see that it has surpassed that 230 value, because it is at 230 angular position is there and it has crossed that 230. Okay, again I will go clockwise to 150 degree. Again you can see it has surpassed. Now I will go counterclockwise. Now I am at 150 degree. I will go counterclockwise to 290 degree. You can see the direction of rotation has changed also. Now I will go for 210 degree. I have moved clockwise. Now it is trying, Now counterclockwise to 300 degree. You can see the direction of rotation is also changing. So the command is 300 degree and it has almost reached 300 degree nicely. So you have seen that yes, the motor unit is obeying the orders. Now we will concentrate on voltages that are developed at certain points in the board. So I will be concentrating on the board now. We will watch the voltages at different points. Okay, I hope it is clear. All right. Now you see the ground is connected, or I will be using another ground, this ground. Okay. So I will give certain reference signal and let us see what is the voltage. that is developed at point 1 because of the reference signal. I hope the voltage is visible. Maybe I can arrange one. It's better. Now you see, the present position of the angular command is 300 degree. So let us see here what is the voltage. There are some disturbances because of this very precision system, you know. So you can see it is 9.72 volt because of that angular position of the command shaft. Now what is the feedback voltage? You can find almost equal, and that's why the error signal, it is very negligible, and you can see there is not much gain. Okay, 1 point something will be the gain factor because it is 0.31 and it is 0.51. Okay, so that much gain is not sufficient to drive the motor. Now you will see that I will keep my knob at this feedback voltage and I will change the angular command. You can see the feedback voltage is changing. Okay, so I will go to the error block and again repeat this activity. I will change the angular command. You can see the error signal is trying to catch the 0 value. Alright, I will again do the same experiment. It is changed. You can see a significant error was generated first, but now the error is continuously being minimized because of the feedback signal, because you know this is not changing. So whatever is changing is the feedback signal. I will again change. You can see the feedback signal is continuously changing. Now what is the feedback signal? You can see it is 5.48. Now your reference signal should be very near to that value. You can find. Yes, it is very near to that value. And you can see the error signal. It's negligible. Now see that we had kept this gain factor to be constant, and we have seen the activity of the entire unit, and we have seen that by giving a positional angular position command we can control the angular motion of a DC motor. This is how we have achieved the position control. This is constituting the first part of the experiment 1 of your coursework. Now this is more a conceptual experiment. You can find, you can just rotate the knob, you will see a rotation, and you should not be happy. You must try to understand the underneath theory behind that. Now what we will do, we will try to go for 3 different values of this controller. So you can see initially I will keep the value to be minimum. It's 0. Minimum. Now we will get back to the dial view. So we can find that how the rotation is taking place, how this position control, whether it is getting precise or it is getting worsened. So you can see here, fine. You can see the gain control knob is at its 0 position. Now the angular command is 130 degree. I will go for a clockwise shift towards 30 degree. You can see I have given the angular command. You have to believe me. I have given the angular command from 130 degree to 30 degree. Next I will take this 30 degree to 270 degree. Still you can find there is no movement. What does that mean? That means that with zero gain we cannot achieve the movement or the rotation of the DC motor, because we need to make the signal stronger. Alright, so I will be giving certain value to the gain. Now you can see very weak gain I have given. Let this be position 1 for the gain controller knob. This is, we are performing experiment number 2, where we have to observe the operation at different gain conditions. So you see here, right now we are at the command knob, we are at 270 degree. Okay, now we will be moving to 220 degree in clockwise fashion. It is 200 degree. Okay, I have gone till 200 degree. Now you see that the position control is very poor. Now I will go clockwise to 140 degree. Again you can see the position control is very poor. Now I will go for changing the gain value to its position 2. Now you can see it's perfectly in the center condition. I will just show you. You can see here it is in center condition right now. And now we will give another command. Right at this point we are at 140. I will go for a clockwise rotation and the angular command will be 60 degree. 60 degrees given. Again you can see there is a surface and the nature is maintained that it is not able to perfectly obey the command. However, the situation is better than the initial condition, that when the controller gain was almost nil. Now I will go for clockwise to 300 degree. Almost it has reached. Okay. Now I will go for the third value of gain. You can see here. Now I will make the gain maximum. Okay. Now the present condition is 300. I will go in clockwise fashion to 200. Now you see absolutely 200. Now let me tell you one thing, that till now I was calling this knob to be the gain control knob. I was deliberately making this mistake so that you keep it in your mind. This is not only the gain. This is actually PID function that is compositely performed on this calculation. You can see that now it is at certain value where proportional gain has been increased. You can see that for any movement there will be first an overshoot. Once the overshoot is there, then it tries to rectify the overshoot and come back to its command position. Now you see I am at 200. I will make it 130. You see there is an overshoot, and okay fine, I will make maybe for a different 90 degree. There is an overshoot and again it is trying to get back to its own condition. So by using this knob, we are actually controlling in a composite manner a proportional controller. You can see now the value is 220. Can you see that? So here we are using a PI controller, so that it can calculate the error, it can give necessary gain, and we can finally come to the stopping condition. The final reading, let us go back to 300. Can you see that? So okay, this is all about this experiment. For any of your confusion or query, kindly let us know so that we can get back and have a discussion on this and your confusions are cleared. Thank you.